In order to talk about the conditioning of the linear system problem, we need to identify the data for the problem and then the solution. So when we're solving AX equals B, the data is the matrix A and the right-hand side B, and the result is the vector X. So we want to see what happens to X, how does X change when A and B are perturbed. All right, so it's a little bit easier if we consider the perturbations one at a time. So let's first look at perturbations of B only with A fixed. So if B is perturbed by an amount delta B, so this is perturbed input, and A is left alone, well, we know that X is going to have to change. So this is the perturbed output. Okay, so if we multiply out that equation, we have A times X plus A times delta X. Delta X is one symbol, meaning a vector, is equal to B plus delta B. Well, we know that X is a solution of AX equals B. That's the solution of the unperturbed problem. So those two sides cancel each other out. So what we're left with is A delta X equals delta B, and if we take that and solve for delta X, it's easy to do so. Delta X is just A inverse times delta B. So if we want to look at the relative conditioning of this problem, right, we look at the relative change in output over the relative change in the input. So this is the first time we've had to deal with a problem that doesn't have scalar input data and output data. So you have to be a little bit more careful about what we mean. So the change in the output is delta X, and the original output was X. So in the numerator here, we have delta X over X, but we want to know the size of these things, so we take norms. Right? It wouldn't make sense to divide the vectors themselves. What we're doing is taking the relative change as measured by the norms. Similarly, the input was B, and the change in the input was delta B, so that gives us the norm of delta B divided by the norm of B. Okay, so the next step, we substitute in for delta X from here. Okay, and we just put things into a simpler fraction. All other three terms are the same as before. Now we're going to use the fact here, this is turning into spaghetti, I'm sorry, but here we're going to use the fact that the norm of A inverse times delta B is less than or equal to the norm of A inverse times the norm of delta B. Okay, so again, here is why we wanted to use induced matrix norms. They are what give us this special property that make it easy to analyze what's happening. Okay, with that substitution, the delta B's in the numerator and denominator completely cancel. So now we're left with A inverse, norm of A inverse, times the norm of B over the norm of X. Okay, now in the next step we're using that the norm of B, well, B is the same thing as AX, and again we use inequality, norm of A, norm of X. So now the norm of X cancels out in the numerator and denominator, and what we're left with in total is norm of A inverse times norm of A. Simple, beautiful little formula that is an upper bound for the relative change in the output divided by the relative change in the input. So that's the full analysis for what happens when we perturb the vector B. Now, when we perturb the matrix A and do the algebra, we get a similar result. The steps are shown in the book. I won't go through them again here. There's a couple of extra steps. There is one key difference, which is that when we do the perturbation of A, and we have a term like delta A times delta X, okay, we have to use a little fanciness and say that we're going to make small perturbations. In fact, we're going to make infinitesimal perturbations. And the product of those two really small things is incredibly small, and they're going to be neglected. So to make that work in a mathematically rigorous context, you have to talk about taking limits and doing things the right way, similar to the way derivatives are defined properly. We won't go through all the steps, but suffice it to say that when you do it properly, you get exactly the same upper bound, norm of A inverse times norm of A. And so what we conclude is that the relative condition number for mapping either B or A to the solution X is norm of A inverse times norm of A. And that's what we define as kappa of A. It's a definition of the condition number of a matrix. So we talk about the condition number of problems normally, but here we're saying that to every matrix we can assign a number, norm of A inverse times norm of A, which is what we call the condition number of that matrix, and that number also serves to be the condition number of the linear system problem. Just as a technical point, if A is singular, it has no inverse, so we defined the norm of the inverse to be infinite in that case. It's like taking 1 over 0. Okay, so with all of the above, we have everything that we need to have proven a theorem. We've just rewritten the change in output over the change in input by putting the delta B over B on the right-hand side. So the first line of this theorem is exactly what we derived above. The second line of the theorem, as I say, there's this technicality that we need to talk about infinitesimal perturbations only. Otherwise, it's only approximate. Okay, but the real story here is if the perturbations in the input, right, either the delta B over B or the delta A over A, if those are due to floating point arithmetic and double precision, okay, we can expect them to be of size epsilon sub m, roughly speaking. And so as an estimate, the relative error in our linear system solution should be bounded by the condition number of the matrix times the accuracy of our arithmetic. And that means that if the condition number of the matrix is bigger than 1 over epsilon machine, then basically you might expect the relative error to be 100%. In other words, there are no digits correct at all. So really, for practical matters, a matrix whose condition number is greater than or equal to 1 over epsilon m might as well be singular to the computer. So what we see here is that in exact mathematics, singularity is, well, it's a singular property. I mean, you either have it or you don't. It's binary. But when you have fuzzy numbers, like we have for floating point arithmetic, suddenly it's not so binary, clear-cut. There's such a thing as being singular, but there's also such a thing as being close to singular. And if you're so close to singular that the condition number is greater than 1 over epsilon machine, well, it's just as bad as being singular as far as the computer is concerned. Even if your condition number is less than that, if your condition number is 10 to the 6th, then you would expect to lose 6 digits in your answer as compared to the input. So for example, going back to polynomial interpolation, if we form a van der Waals system to find the coefficients of the polynomial interpolant, remember the van der Waals system here, let's say we have 21 points in T. That's defined here. So we can fit a polynomial of degree 20 to it. So we take those values of T and stuff them into the columns of a square van der Waals matrix. It's 21 by 21. Then that system VC equals Y defines the coefficients of the polynomial, which interpolates the data Y. So here we're going to use van der in MATLAB to compute the van der Waals matrix. And then we're going to fit to the data T squared. Well, if we're fitting a polynomial of degree 20, right, C20, T to the 20, and so on, plus C2, T squared, plus C1, plus C0, and if that's supposed to approximate the polynomial T squared, well, we can do that exactly, right? We should get C2 is equal to 1, and all other C sub i's equals 0. That's a perfect fit. So that's the exact solution. But when we actually do it in MATLAB, we get this warning. The matrix is close to singular. And this R cond, R stands for reciprocal. So this is an estimate of 1 over kappa of A. So if that number is machine epsilon or smaller, that means the matrix might as well be singular. And indeed, when we look at the answer, these CIs are not anywhere close to 0. All right? This one's 0 only to 1 digit. So practically no accuracy here at all. If we scroll down to the one that's supposed to be 1, it is apparently 1 to at least 5 digits, but probably not all 16. Nevertheless, the other ones that were supposed to be 0 aren't really close to 0. If we want something more accurate than the estimate from R cond, the reciprocal of the condition number, we can use this MATLAB function cond, which computes the condition number using matrix 2 norm. And for this case, it's just about 10 to the 17th.